Okay, so we're doing a second order example here, an RLC circuit, and we're going to go through the two steps that I like to use to solve the circuit. I like to think of it as a time before zero, right? Think of this as zero. This will be 0 minus, this will be 0 plus, right? Should have learned that in calculus. And this will be our 0 minus circuit. So this is before the switch is flipped, right? So you're going to have, stop. You're going to have the switch closed on this side for 0 minus, right? Because this arrow is telling us when the time it's 0, it's going to flip over to this side, right? So for this circuit, for 0 plus, for the right hand of 0, the circuit will be like that. So for 0 minus, our first goal is to find the initial values, right, across the inductor and capacitor. That'll help us figure out a formula to define the transient state of the circuit as time passes. So, to figure that out, we need to figure out the initial values across the inductor and capacitor. So, I sub naught, or I naught really, what would that be? Well, when we're referring to I naught, we're referring to the inductor. And when we're referring to V naught, the initial voltage, right, we'll do minus to really show you what we're talking about. Then this is going to be capacitor, inductor, right? So for the inductor, we know if it sits for a very long time, right? For 0 minus, the inductor will be a short circuit, so it's just going to be like a wire. And is that really 1 second? Had to change one thing. The value of this resistor should be 10. Okay, so the initial value, right, as I was saying, the inductor is going to be short circuited, right? So in reality, if this sits for a while, this will be just a wire, right? So we need to find out the situation in which the current through here is for 0 minus when it's acting like a wire, basically. So if you do 20 divided by 10, you get 2 amps, right? And that's going to be the current going through here. And that is what our I naught to the left side of 0 is going to be, 2 amps. Now what about the voltage initially across this capacitor? Well, the voltage is only going through one resistor, right, and then it goes through the capacitor and then to ground. This is ground. We'll make that noted. So since it's only one resistor, right, it's kind of a rule that all of the voltage will be after that resistor. So since there's only one resistor in between the capacitor and the voltage source, there's going to be a total 4 volts sitting on that capacitor. It's going to be fully charged to 4 volts as it sits for a very long time. Okay. And it's good to note that capacitors, when sitting for a while, become an open circuit, the opposite of an inductor, right? Because for a lot of situations, capacitors and inductors are opposites of each other. Okay. So our main goal is really to find this arrow here, which we're going to call it I as a function of time, or the transient state for the inductor. Okay, since we found those initial values, let's go to the next part of the problem. This is for 0 plus. Now we need to write an equation for this, and this should be not 20, but 10. So, now we need to determine I as it goes to infinity, and voltage as it goes to infinity. And we're referring to the inductor here and the capacitor. Well, as this goes to infinity, this will be short-circuited, and this will be open. And if we were to travel from this power source past this resistor, it's going to take the path of least resistance as it goes to ground. This is going to be ground. It's going to take this path, right? and go to ground. It's never going to go to this capacitor anymore as it goes to infinity, right? It's going to go to ground, the path of least resistance. So, it's going to be 2 amps here, because as 20 divided by 10 we get 2 amps. That current is only going to through that inductor as it goes to infinity. We're having 0 volts here across that capacitor because as it's initially going to be 4 volts, right? But it's going to discharge and go to 0. Okay, so now let's write our formula. So since this is an inductor and a capacitor in parallel, there's a proof to do it. You could do a KCL at this node and plug in what an inductor and a capacitor and resistor is equal to for I, and find your values that way and set up as a differential equation. Or you could just do, um, if you ever get a textbook, it'll tell you negative alpha plus or minus the square root of alpha squared minus 1 squared. Alpha is going to be equal to 1 over 2 times the resistance seen by the capacitor. 1 will be 1 over root LC. Okay. And then you just really plug in the values. So the resistance seen is basically going to be the resistance seen by both the inductor and the capacitor. And obviously, right, if you were to think about it conceptually, define resistance seen by anything really. You can kill the other sources. Power sources get shorted. Current sources get opened. If you were to take this point up here and travel to the point below it right here in one single line, taking the shortest path, you would get 10 ohms there, right? And if we do that for the capacitor, the shortest path, not going through that inductor because it's an inductor, but going through this resistor and going around to the capacitor. I don't know why I did that. But typically, the resistance will be equal for both the inductor and the capacitor. But in this case, it's really going to be the resistance seen by the inductors. The easiest way to figure it out from point A to B, right this way. Right. So we know the resistance is going to be 10. You should probably find a few other problems and test that out. Alright, so for 1 over 2 RC, 2 times resistance times capacitance, we get 1, which sounds about right. And 1 over root LC. You get some really nasty number like 2.236. Right. So when you take 1 squared minus this weird number squared, we get negative 4. So we're going to get 2I plus or minus negative 1. Alright, plugging that into the formula. Alright. So this is one of the cases where you have to do, I think, Euler. Euler made this. When you have an imaginary number like this, you can set up as the following. Alpha being out here, negative 1. This is the negative 1. X, it's going to be negative 1 times x. Inside we have C1 cosine of whatever this number is here, 2x, well, it would be t, because this is all a function of time, plus C2 sine of 2t. Okay. Okay. So now that we have our general formula, we now need, let me do this really quick. Alright, so since we're finding I of t, what we're plugging in to find this function as a I as a function of time, we're plugging in this as our initial condition, our IVP, right? If you have initial value problems, like from differential equations. Oh, my bad. That's not I at 0. This is I at 0, right? This is going to be our I at 0, right? Or IVP. But we also need to find DI, DT, to find our initial value for I prime at 0, right? So that's going to be equal to the voltage initially across the inductor divided by its inductance times di, which we'll give as ditt, right? Plus, right? So it's the initial voltage, right? So the initial voltage will be the voltage across the capacitor that's going across the inductor. So it's going to be 4 volts, since that's what's going to be for 0 plus across the capacitor. So it's going to be 4 divided by 4, so it's going to be 1 amp. Okay. So we're going to set up our equation to find our constant C1, C2. It's going to be 2 is equal to C1 plus C2, right? Because this is for I of t at 0 plus the final value for the current, which is 2 amps. So this is going to be 0 is equal to C1 plus C2. That's what we get. Okay. So now we need to solve for the other, since we know that's going to be equal to 1. And we need to find I of t prime. We need to grab the derivative of this function. So we're going to get, let's do the product rule, negative e to the negative t. We grab the derivative of this first, and then we have to rewrite all of this really quick. Plus c2 sine of 2t. Then grab the derivative of the inside function and add it to it. E to the negative t. The derivative of cosine is going to be negative 2c1 cosine of 2t plus 2c2 cosine of, no, this becomes sine, my bad. Cosine of 2t, that's written pretty bad. But, okay, so when t is at 0, right, this will disappear, this will disappear, this will disappear, this will practically disappear. So we're going to pull this down. We get a negative c1 cosine of 2t plus 2c2 cosine of 2t. Oh, and it's good to note that I kind of forgot this. So for our first equation, when I of t is at 0, right? This will be 0, or this e will be 1, cosine will be 0, so you keep our c1, right? But our c2 has at 0 is going to be 0. Sine at 0 is 0, so c2 is going to disappear. So we know c1 is equal to 0, right? And for the second equation, we know negative c1 cosine of 2t plus 2c2 cosine of 2t. We know c1 is 0, so this is going to disappear. So we have 2c2, right? Cosine of 0 is 1. is equal to 1. So 1/2 is equal to C2. So now let's plug our values into our new equation. So we're going to have C2 is 1/2, right? And we're going to have sine 2t e to the negative t is equal to I is a function of time. This is our final equation. This is our answer, right? And if you go to uh, this here, he also should have gotten that is the answer. And I can't forget this part. When you're setting it up and as a final value, you add that to it. Never forget that. 2 plus. The formula is going to be I final plus whatever your C1 plus C2, uh, your general solution, right? Like you'll have C1, let's say e to the negative 5t plus C2 t e to the negative 5t plus I final. Like I final will always be over here in your final answer, but usually it'll be 0 in most cases, but for this one, it's because it starts off at 2, right? The inductor starts off at 2, so you have to have that plus 2 as it travels. It'll be, and then what it'll look like is, if it starts off at, we'll call this 2, right? Sine wave, it'll deplete slowly. That was horrible. It'll deplete slowly and eventually diminish to 0, right? That's what it's going to look like. Yep. So if it's a sine wave, I think it might start like this instead, but you get the general idea. So yeah, that is how to do the second order for this problem.